Cool. Okay, so welcome back to CS580 computer graphics. So last time we discussed some kind of the basic terms, the terminology about the radiometry and the photometry, which are basically some kind of the ideas in terms like introducing some kind of the some measures and also the units about the illumination for the lighting. So we mainly discussed this before the concepts. Like the first one was basically about the flux, which basically indicates the power delivered by the light. And then there are basically three subsequent the concepts. What the first one is basically intensity. Radiant intensity basically indicates the flux per the unit solid angle. So we also discussed the idea of the solid angle. And also in contrast to that, the irradiance was basically the flux per unit area. So which is more about basically measuring the light, which is like coming into the some specific point over the surface. And the radiance was basically the flux per unit area and also the per unit the solid angle. So we saw basically the kind of the quantity of the light which is delivered for the given the ray of the light. So we are basically having these kind of three D concepts. And one, there are some kind of the multiple important things. Like one also important thing was that the radiance was specifically defined as kind of the flux per unit solid angle and also the per unit the projected area. So we are basically having the cosine theta term here. So we discussed like why we are having this term in the last lecture. And based on this definition of the radiance, we could also compute the radiance in terms of like having this kind of the terms of the differentiable irradiance, which is basically defined as kind of the radiance multiplied by the cosine theta and also the differential of the solid angle. And based on that, we can like, given the information about the incoming radiance from all the directions, we could basically calculate the radiance for it to be point. So this was basically the basic idea in terms of like seeing the relationship across the different kind of the quantities of the measures of the lights. So what we also could see is that, if we have some uniform radiance from all the directions, from all the incoming directions, then we could basically derive that the radiance is also defined as kind of the L times the pi. So when the L is basically the uniform radiance from all the directions. So we should be able to basically do this kind of all the calculation based on this kind of the concepts of these the measures. So what we are going to do in this course is basically like measuring, calculating all these kind of the measures given the scene and the light information. So we're gonna get into the basic idea of the rendering equation today, and then we're gonna also start to see how we can exactly calculate all this kind of thing. So as you can see, like the rendering is basically all about basically calculating the radiance for each of the ray. So if we basically have the radiance information for each of the ray, then we are basically collecting all this information to basically calculate the final color information for each of the pixel. And for that, as we also discussed the idea of the ray tracing, basically we will need to be able to basically calculate the kind of reflection of the surface. So the basic idea is that when you basically have some kind of the radiance information for all the incoming lights, they are already collected at a certain point of the reflection over the surface. And then based on that, we will be able to basically update kind of the radiance information for all the outgoing directions. So for every kind of the point, for the incoming direction, for the outgoing direction, we are having some kind of the different kind of the quantities, different kind of amount of the radiance, because the radiance will be basically changed depending on the reflection that we are making for each of the surface. And also each of the surface will have some different patterns of the reflection. And this kind of the pattern of the reflection is basically defining the property of the material for each of the surface. So that's also what we are going to discuss in the rest of the course in terms of how we are going to define the reflection in the models. So there can be basically very different ways to basically defining this kind of some reflection in the models, depending on the property of the surface that we are going to define. For instance, like if we assume some kind of the perfectly flat the surface without any kind of the bump in any kind of the micro level, then what we can assume is that we can say that, as we also learned in some kind of the some high school kind of science kind of the course, when you have this kind of the incoming the light direction based on the surface normal here, we can directly calculate what will be the direction that the light will be reflected to. So this will be the case that we are having the ideal the specular the reflection. So when you have some kind of, assuming that we're having some kind of one single the incoming the ray, which is like reflected over the surface, then based on this kind of the incoming direction, I'm not sure whether you can see the mouse point. Yeah, so based on this kind of the incoming direction and also the surface normal, we can basically define a kind of the plane defined with these two vectors. And then we can also calculate the outgoing direction of the light based on the angle between the this incoming the ray direction and also the surface normal. So we need basically calculate the outgoing direction by just making this angle between the incoming ray and the normal and also the angle to the outgoing ray to the normal to be the same. This is basically the case that we are exactly transporting all the light information coming from the incoming the ray into this specific the outgoing ray. So this is the case that we are having the perfect the spectral reflection, which is also assuming that the surface is perfectly flat. There is no bump over the surface. So this is kind of some kind of characteristics that we can see for some kind of the materials like the metals and the metal kind of the materials, right? So this is the case that we're having the spectral reflection. And also there can be some other cases that we are having some ideal, some diffuse reflection, which is assuming that in the micro level, the surface is having like lots of the bumps, which means that we don't know what exactly what will be kind of outgoing direction for the incoming direction, because like the surface is very bumpy at the local point. We cannot see all the bumps, but in the micro level, we are having some bumpy kind of the surface at the point, which means that the ray can be reflected into any random kind of direction. And when you assume that this kind of the probability or like being reflected into any of the direction is kind of the uniform, then we are basically getting some kind of the ideal, some diffuse reflection. Those are some of the cases that we can see in the clay that you can see here, or some kind of the wooden material. For those cases, we're gonna see some kind of the ideal diffuse reflection. But for most of the cases, we're gonna see something between the perfect spectral reflection and the perfect diffuse reflection. So one of the example might be like having some kind of the glossy spectral reflection, which is not exactly basically reflecting the incoming ray into this specific the outgoing the direction, but having some kind of some distribution near that specific the outgoing direction. So even have this like this incoming ray, the ray can be not like reflected into all the directions uniformly, but basically having this specific direction, but can be basically diffused a little bit into some kind of near other some kind of directions. So this might be kind of like more typical the cases that we can see in the many some plastic shapes or many kind of some other materials. And there are also very special types of the reflection. One of the cases might be the retroreflective cases, which is the case that the light is basically reflected back to the incoming direction. So those are very special cases for that we can see. So many kind of the traffic signs are basically having this kind of the material, so that the drivers basically can notice this kind of the signs in the nighttime. So those are also some special cases of like retroreflective material kind of cases. So those are basically all the things that we can define. So we can define this kind of the material properties by defining the reflection functions. So depending on how we define the reflection functions, we can have this kind of the different kind of the appearance of the shapes, as you can see here. Like those are the cases that we are having some perfect the spectral reflection, perfect diffuse reflection, and also some other types of the reflections depending on the material the property. So what we can do is that for each of the material, the real the scene, the kind of the real the objects, we can really measure this kind of some reflection the patterns, which is described as kind of some reflection the function. And if we basically simulate the same reflection in our rendering the pipeline, then we can really have this kind of same the appearance of some kind of real the materials. So this is the main idea. So how exactly we define this kind of the some reflection dependency into the function? So what the thing is then for the many of the practical cases, this kind of some kind of the reflection patterns are basically characterized as kind of the ratio between the differential the irradiance, the incoming the irradiance, and also the differential the outgoing the radius. So this is a little bit different with like what we can easily imagine. So we can consider like having the ratio between the differentiable, the incoming irradiance, and also differentiable, the outgoing irradiance. But actually, for most of the materials, the characteristics are basically captured when you see the ratio between the differentiable, not the incoming radiance, but the incoming, the differential, the irradiance, and also differentiable, the differential, the outgoing irradiance. So when you see this kind of the ratio for all the directions, we can basically, when we also have the function for this, we can basically somehow characterize this, basically express the property of each of the material. So this is the function which is called the BRDF, which is stands for the bidirectional the reflectance distribution function. So BRDF would be basically the function, the name of the function that you basically hear from many places in the computer graphics, the kind of literature. So BRDF is basically the function which is taking both the incoming direction and the outgoing direction. And this incoming and the outgoing direction can be also represented with the speaker the coordinates, right? Which means that this is the function which is taking the four numbers, like two numbers for the incoming direction and another two numbers for the outgoing direction. And this function is basically describing the ratio between the outgoing irradiance compared to the incoming the differentiable irradiance. So we're gonna have this kind of the ratio. So basically here the idea is that for any kind of the material that we want to express in our rendering the pipeline, all the material now can be represented as a BRDF. So that's the main idea. And what we are doing in the rendering the pipeline is that basically we are calculating the reflection for each of the point in this way. So what we can see is that for kind of the information for the incoming the radiance for all the directions, now we are calculating differentiable the irradiance in this way, and then basically taking the integral of the some kind of ratio, like the how much of the differentiable the irradiance for each of the incoming direction will be reflected into the each of the specific the outgoing direction is basically represented by this BRDF. So when you basically take this kind of the weighted sum, weighted integral of the differential of the integral with this kind of ratio described by the BLDF, and then we also, when you add up some kind of the outgoing the radiance, which is like purely emitted from the surface. So it's especially for the cases when the surface is also emitting some kind of light as well. When you basically sum all these kind of things, that basically describes the outgoing the direction, the radiance for each of the specific direction. So this is basically the rendering equation, which is basically calculating the reflection for each of the point. So yeah, so you can see that this part is basically incoming the radiance, and also we are taking the differential of the incoming the irradiance by multiplying the cosine theta here, and then we are taking the weighted some kind of the weighted the sum of the differential of the irradiance for all the directions with the ratio which is described by BLDF. Then this basically describes the outgoing irradiance for the specific direction that we are considering here. And when you also add up some kind of the emitted the radiance as well, in the case when the surface is also emitting some kind of a light, then we can basically calculate this kind of reflection. So as you can see, so we're gonna get into some more details about how exactly we can calculate all the things from the ray tracing the pipeline. And you can, as you can guess, this is quite complicated kind of process. And also here, the key thing is basically how we can calculate this integral here. So as you can see, like the rendering equation is basically all about basically computing this integral. And also this is the case that typically we cannot have any kind of the analytic solution for the integral. So we need to have some kind of some numerical approach in terms of like approximating this integral here. So basically we need some kind of the tricks to approximate this computation. So that's basically what we are going to discuss for the rest of the course, how we can calculate those kind of things. But before we get into some more details, do you have any questions on this? Great. Yeah, so what we are going to discuss mainly today is basically how we calculate this kind of integral in the case that when we don't know the analytic solution. And for that, we're gonna get into the basic idea, which is about the Monte Carlo integral, the method. Is there anyone who has heard about the Monte Carlo method before? Is everyone familiar with the Monte Carlo method? Uh, question. So if you know well about the Monte Carlo method, yeah, this will be very basic introduction for the Monte Carlo method. So these things might be very quite easy to follow. But for some of the people who didn't really study those kind of stuff, let's briefly go over these things. So actually, the things that we are going to discuss for today is more about some kind of the very simple the math. Sorry, there's no graphics here, so just like doing some kind of the calculation. So let's get into the basic idea for the Monte Carlo method. So basically, why is it called the Monte Carlo method? So this is basically the basic idea in terms like calculating all the integral with some kind of a stochastic desampling, which was basically primarily developed by the Polish mathematician. I'm not sure how I need to pronounce this name, but Stanislaus Ulam. And he basically named this method as the Monte Carlo method, inspired by the Monte Carlo casino in the Monaco. So which is basically doing some kind of the gambling things. So before we get into some more details of this, I guess most of you obviously they took the introduction to statistics the course. Well, let's briefly get into some of the basic idea here. So when you talk about the random variable, which is basically indicating a value, which is obtained by sampling from a kind of the probability density the function, the distribution. When you also have some kind of the function of the a value, the random variable that becomes another the random variable as well, right? And then we can also define the expected value of the function, which is also defined with the random variable, which is like literally some expected value for the function. So which is actually defines some kind of the weighted sum, weighted interval of the function value multiplied by the probability for each of the random variable. And we can also define the variance, which is the expected value of the difference between the function value and the expected the function value. So these are all the basic things, right? And also from the property of the expected value and the variance, we can see those kind of things. So when you have the expected value of the function multiplied by a scalar, which is the same as kind of like having the expected value multiplied by a scalar after that, right? For the variance is different in terms of if you have the scalar term here, then it's the same as you are taking the variance first and then multiplying the square root of the scalar term here, right? And also those are basically also coming from the definition of the expected value and the variance, especially like the sum of the variance of the sum of the function is the same with the variance sum of the variance of the function only when all the random variables are basically independent of each other, right? So what happens if we have the variables that are not independent of each other? Then what should we do for those these terms in the first term? I mean, quick question that whether you have checking whether you have some kind of a background in the statistics. If the random variables are not independent to each other, then how should we change the first the formula here? Yeah, I mean the answer is that we need to basically add the covariance term, right? So for when all the random variables are independent of each other, then the covariance becomes zero, then we don't need to add the covariance, right? Otherwise, we need to basically have some kind of the covariance term in this case, right? And from all these kind of the definitions and also the properties of the value and the variance, that we can also derive that the variance of the function becomes the same as kind of the expected value of the squared of the function minus the squared the expected value of the function. Right? So those are all these basic things for the statistics. I'm assuming that you know all these kind of things. Just in case that you're not familiar with those kind of things, I also posted a link in our Slack workspace that provides like some more some kind of introduction of those kind of some basic things. So please check out the link on the Slack workspace to just in case that you don't have the background of those kind of things. Okay, so actually the Monte Carlo, the integral is basically very simple the idea. So let's get into the simplistic case. So let's say we want to compute the 1D integral of the function f here in the range from the a to b. That what we are going to do is that, so this is the case that we are assuming that we cannot derive the analytic solution for this integral. So we want to take some kind of the numerical approach. So one of the ways that we are taking the numerical approach is that we are basically having some lots of the independent and the identically distributed the samples over the range from the a to b. So basically here, what we mean with the independent and the identical distributed sample is that we know the meaning of the independence, right? The identical distributed sample basically means that typically this means that all the samples are from the same probability distribution, right? So for those cases, what we do is that instead of like having some kind of analytic form of this integral, what we are going to do is that we are going to take this kind of the IID samples as many as possible in the range, and then we are taking the sum of this the function value, and then finally we get this kind of the estimator of the integral. So as you can see, this becomes some kind of approximate of the 1D integral. And then we can also see like why this is kind of the good estimate of the integral. And one of the reasons that why this is kind of the good the approximate of the integral is that if we take the expected value of the estimator, then we can actually easily see that the expected value of this the estimator becomes the same with the integral here. So let's quickly prove this. Based on the properties that we have seen in the previous slides, you will be able to see that actually the expected value of this estimator is equal to the integral. So can you quickly prove this? Yeah, I mean, we can see that actually basically follows the rules of the lab numbers, but I mean, it can also basically derive exactly how why the expected value of this estimator becomes the same with the integral. Maybe you can write down the formulation. So by the way, I'm not sure whether you can see my the web page, but all the materials that we are discussing today, which can be found in this PBR the book. So this is the book titled like Pitch Poly Based Rendering. And the good thing is that this is like obviously one of the most the famous big book about the ray tracing, especially all the like things about the graphics. And the good thing is that everything is publicly available, so you can check out all the materials in the book in the web page, even without like buying this book. So you can check out some more details in this website, and you can also basically follow some of the details that are introduced in this textbook. So while we are posting your answer, probably we can derive that these two are exactly the same based on the property that we discussed in the previous slide, right? So you can see that like these are all the same, and what's the default? Yeah, so we are seeing that the sample is like a sample from the uniform distribution, right? Which have the probability of the 1 over b minus a for any point over the domain. So we can cancel this probability with the b minus a here. Then we end up getting this basically saying that the expected value of the function becomes the same with the true value when we want to see it, right? So this is basically very natural idea in terms of like approximating the quantity we want to see, basically integral. And we can also see that mathematically the expected value of this estimator also becomes the same with the integral that we want to see. So this is really good. And also the good thing of like this simple idea is that it can be extended into any dimension. So we have seen this kind of like example in the 1D integral, but for the any kind of the some multi-dimensional integral, for example, in the 3D case, what we need to do is that we can simply also sample any kind of the points in the given the domain with either uniformly with some kind of or using some kind of the some random probably that's the distribution. We can also discuss in the later the slides. And based on that, we can basically have this kind of the estimates of the integral in this way. So the thing is that whatever kind of dimension of the space that we have, we can choose the number of samples arbitrarily, regardless of the dimension of the function. So that's also kind of the good point in terms of that. The extension to the arbitrary dimension is very straightforward. So this is like very simple the idea. So let's briefly see what we can do with this kind of the Monte Carlo sampling and Monte Carlo method. The basic and the famous the example might be computing the area of the circle or the computing. Actually, we can apply this the idea to compute the area of the any region or volume in the any kind of the some kind of objects in this 3D space. So let's think about this case. Like we consider a circle where any kind of some region in the two-dimensional space, which is denoted as the omega here. And what we want to do is that we don't know, let's assume that for the circle we obviously know, but let's assume that we don't know some kind of the analytic, the way to calculate the area of the specific given the region. So what we are going to do is that we are going to define the axis align the bounding box for the region, the given region, which is having the range from the x0, y0 to the x1 to the y1. And given this kind of the domain and the region, we are going to use the Monte Carlo method to compute the area of the given the region, the omega here. Then what we kind of the basic way that we can utilize the Monte Carlo method to compute the area of the given the region. So let's think about this. So the first thing that we need to do is basically how we express the area of the region as kind of the form of the integral, right? So we should be able to basically define a function and define the area as kind of the form of the integral. And then we will be able to see like how we can really compute the estimate the integral using the Monte Carlo method, right? So basically what we can do, we can see in the formulation is that we can first define a function like this. So we are defining the function f like this in terms of that it becomes the one when the query point is inside the region and zero otherwise. Then the area of the given region will have this kind of integral form, basically taking the integral of this kind of function in the given the range of the bounding box, right? And from this kind of the Monte the estimate that we have seen in the kind of the previous slide, we can have this estimator. Then we can also see that this estimator will also have the expected value, which is matching the given the area of the region, right? So here basically what we can see is that here the n is the number of the samples, and we are also having the sum of the function. And since the function is defined like this, then we can see that the sum of the function becomes the number of the points that are basically included in the given region. And this term on the left-hand side becomes the area of the bounding box. So what this basically means is that once we basically sample lots of the points in the kind of given the bounding box, we can also count how many of the samples are basically included in the given region. And if we compute the ratio of the inside count and also multiplied by the bounding box the area, that becomes kind of the estimate of the area of the given region. So that's also very straightforward way to basically estimate some kind of the region of the kind of the object in the 2D space. That can be also be done in any kind of arbitrary dimension. And also the good thing is that we can see that this kind of simple way, the estimate of the integral can be kind of the good in terms of that the expected value basically matches the output that we want to see, we want to get. Is this clear? Any question on this? Clear. So this is like very simple idea of the Monte Carlo method. And here the question might be is that, do we really need to take the samples from the uniform distribution? So what if we basically samples which is not following the uniform distribution, but some kind of the any arbitrary some probability the density function? So in this case, like, I mean, we can also have this kind of the same the Monte Carlo the estimate. So we had the B minus A here, which is basically the same as basically 1 over the probability T here. So when you also have some kind of the non-uniform the random variables, instead of like multiplying the B minus A here, we can simply multiply the 1 over the probability here. So that becomes the same kind of the types of the Monte Carlo estimate for the same the interval. So let's also briefly check out whether this some generalized version of the Monte Carlo estimate also has the expected value, which is basically matching the given the interval. So let's quickly check this out. Did everyone get the same results with this? So actually it becomes more obvious, like why we had the b minus a come here. Actually, it was just the dividing the function value by the probability for each of the random variable. Then when you have this kind of like 1 over the probability of the random variable, that becomes like cancel out here in the third the rule, and then we're gonna get that the expected the value of the estimator becomes the same with integral like this. Clear? So this is like good in terms of that it's quite like intuitive way that we are approximating in kind of interval with some kind of the discrete number of the samples. And also what we can see is that the first thing is that we can see that the expected value of these estimates basically matches the output that we want to get. So that's kind of good. And also whether we have some kind of the uniform samples or the non-uniform samples, we can also have the same type of the Monte Carlo estimator for the integral. So that's kind of a good thing. So now we can say, like, for any kind of integral, we can use this kind of the Monte Carlo method in terms of like getting some kind of approximate of the value that we want to see. But here also the question is that then how fast the kind of estimator converges to the true value that we want to get. So by the way, this is like all the cases that we are getting the results that the expected value of the estimator basically becomes the same with integral. So that's the case that we call unbiased. We can also see the biased case as well. But before we get into the biased case, let's also briefly talk about the variance, which is the expected value of the error. So basically, the goal is to also minimize the variance in terms of that the estimator converges like faster to the true value. Then here the question is how fast does the estimator converges to the true value? So then we will need to basically measure some kind of the variance, right? So what we are going to briefly see is that, like, let's first see some kind of the simplified kind of the version of the estimator, which is just like taking some kind of the average of kind of the given these samples. So many of the kind of the Monte Carlo, the estimates becomes like have this kind of the form, having some sort of the average of the some kind of the samples. Then if we actually check out the variance of this estimate, in the case that when each of the IID samples has the mean of the mu, and also the variance of the sigma d squared, if we compute the variance of this estimate after doing all this kind of derivation based on the rules that we discussed in the previous slide, we can see that actually the variance of this kind of estimator becomes like proportional to the one of the number of the samples. It is clear. So what we can see here is that the variance of the estimate becomes like inversely proportional to the number of the samples, which means that when you see the variance basically decreases linearly when you basically increase the number of the samples at the end. So when you also see that the variance is the same with the square root of the error, we can basically also say that the error is basically sort of the proportional to the number, one of the square roots of the number of samples, which actually is kind of quite slow the convergence rate. So if we can actually have some kind of the faster convergence, that can be better. So actually, we are going to consider not only basically some sort of the correctness of the estimate, whether the expected value of the estimate is really matching some kind of the output that we want to see, but also how fast that we are basically getting into that number. So how many samples do we need to basically closely approximate the given the outputs? And this kind of the speed of the convergence, the rate, is basically representative is kind of the variance. But we might also want to consider, so when you talk about some kind of the efficiency of the estimate, we might also consider not only the variance, but also the computation time for each of the sample, right? So let's talk about discuss the efficiency of the estimator in this way. So let's think about like two types of the estimators. Like one is the F1 and the other one is the F2. And those are also kind of some Monte Carlo style kind of the estimator in terms of that their variances are basically inversely proportional to the number of the samples. But the thing is that let's say like the variance of the second estimator has the half the variance of the first the estimator. while the second the estimator takes like 3 times longer to compute each of the samples. Then in terms of the efficiency of the estimator, in terms of getting close to the true value with the samples, which one is the better? So we can also think about like define some kind of efficiency of the estimator by taking care about like not only the variance but also the computation time as well, right? You say like which one is better and why? So let's pick one of them and so think about like why one is better than the other. Yeah, some people say F1, some people say like F2. Well, okay, one way that we can think about this might be is that like let's say like this. So let's say like the variance of the F1 is defined like this. Then the variance of the F2 is the half the variance of like this one. So we're gonna get this for the variance of the F2. But these are the cases that like when you have the same number of the samples, but when you think about like same amount of the computation time, then the F1 will basically 3 times faster than F2, which means that F1 will basically have the 3 times more the samples for the same amount of the time. So when you have the not at the n number of samples, but 3n number of samples, then the variance of the F1 becomes decreased to this. So we need to compare this variance with the variance of the F2 here, right? Then we can say that for the number of samples that we can get during the same amount of the time, we can say that the variance of the F1 basically becomes smaller than the variance of the F2, which means that there is a like higher chance to that we can get closer to the ground truth, the output, the interval, right? So from this analysis, we can say that actually F1 is better than the F2. So this is the case that we are not only caring about the variance, but also the computation time as well in terms of basically somehow assessing kind of the efficiency of each of the estimator. It is clear. So this means that basically when you define the efficiency of the estimator, we can basically define this efficiency in this way as kind of like 1 over not only the variance, but also the computation time as well. So which means that like as we have the higher efficiency by considering the computation time as well, we can check which one is basically more efficient based on the kind of like the number of samples that we can also get during the same amount of the computation time. Is this clear? Any question on this? Well, so based on this, what we can say is that, yeah, we can have the Monte Carlo the estimator, which are basically the unbiased the estimator, which is expected value basically matches the interval. We can also measure the kind of the sort of the convergence rates based on the variance of each of the estimator. And then basically we can pick the estimator, which is giving the expected value matching the output, and also having this kind of the higher the efficiency, right? Explain the F1 and F2 efficiency one more time. So, I mean, you can check out this example first. I mean, so this is the case that, that we are having the two estimators and their the variances. But we are not comparing these two variances. We are actually computing the variances with the number of samples that we can get for the same amount of the time. So when you see that like F1 is basically faster than the F2, so this is the case that F1 is like 3 times faster than the F2, right? Then what we need to do is that we are not taking the n number of samples, but 3n number of samples, right? Then the variance of the F1 basically decreases to basically this amount of the variance, right? So instead of like multiplying the 3 into the F1, we can also divide divide the variance of the F2 by the 3, right? Then this will be the case that we are basically doing some kind of the apple to apple comparison between the variances with the number of samples that we can get in the same amount of the time. Then, I mean, if we consider this kind of number of samples in the same computation time, then we can define the efficiency in this way. So yeah, maybe you can check out this by comparing these two slides. So this is basically kind of formulation, which is not only caring about the variance for each of the estimator, but also the computation time, which basically affects the number of the samples that we can get for the same amount of the time, right? Clear? Any questions on this? Yeah, so those are kind of things. So what we can say might be is that, yeah, when we have some multiple estimator, we can pick one, which is like one unbiased, and which is also giving the best the efficiency. But actually, there are some of the cases that we are having some kind of the estimator, which expected value does not match the value that we want to see. I mean, the value of interval. So those are the cases that we call the biased the estimator. So formally, you can say that this is the case that the difference between these two, the expected value of the estimator and the interval value, this difference becomes like non-zero. So let's think about like one of the famous examples of this kind of biased estimator that you would learn in the statistics course, the simplistic case. So let's think about that we are having some kind of the IID samples, multiple n number of the samples, which are also all coming from the same probability the density function, which is having the mean of the mu and the variance of the sigma squared. The thing is that while we know that all these samples are sampled from the same probability density function, let's say we don't know the variance, right? So we want to have the estimate of the variance of the probability density function. Then what be kind of the best way that we can define such kind of the estimator for the variance? So this is the very basic setup that you would learn in the statistics course. Then the simplest way that we can define some kind of estimator for the variance might be this form, right? This is basically some of the following kind of the definitions of the variance, right? But it turns out that actually this is not the unbiased estimator for the variance. So this is basically the known fact which is named as kind of Bessel's fraction. So how can you check whether this is kind of the biased or the unbiased? So I recommend you to check this out yourself after the lecture. If we basically go down into some more details here, that we can see that the expected value of this estimator can be rewritten like this. And then basically, if we also from the rules of the variance, which can be that the variance can be rewritten as kind of the expected the squared the random variables minus the squared of the expected the value of the random variables, right? From this we can derive this. So you can check out those details. So what you can see is that the first term has the variance plus the squared mean. And the second term has basically 1 over n, the squared the variance plus the 1 over the n times the variance plus the squared the mean. So you can check out that this comes from the definitions of this x bar, which is the mean of the sample set. Then what we can see is that these two are canceled out, and at the end, what we are getting is that actually we get n minus 1 over n times the variance. It's kind of the expected value of this kind of the estimate, right? So while basically this estimate looks very intuitive, it's kind of like getting like estimating the variance. Actually, the expected value of this estimate is actually not matching the variance that we want to get. So in terms of that, we can see that this is kind of the biased estimator. Then how can we basically modify the estimator to get the unbiased estimator? So when you know that this S squared is kind of the biased estimator of this like sigma d squared, then what's the kind of the unbiased estimator? Yeah, I mean, simply just multiplying n over n minus 1, right? So if we basically multiply n over n minus 1 to this estimator, this becomes the unbiased the estimator of the variance. So this is why that we are basically not exactly just simply following some kind of I think there's some kind of typo here. Yeah, we are not using this kind of like form of the estimate, which looks more natural in terms of like estimating the variance. But if we actually want to get the unbiased the estimator, actually we should have this kind of form. This is kind of the case that we are having the Bessel correction to properly estimate the variance of the given some kind of the probability density function, whereas we don't know the kind of the variance. Right? Is this clear? Any question on this? Actually, what we need to see is that so we need to get some very clear the idea what's the kind of the difference between the unbiased estimator and the biased estimator. So when you talk about some kind of the biased estimator, it does not mean that it's kind of some wrong kind of estimate for the outputs. In terms of that, basically, if we increase the number of the samples and to the infinity, so if we have like lots of the samples, which is really like going into some kind of like having some sort of the infinite the number of samples, then we can see that actually this biased estimator also converges to the true output, right? So when you talk about the biased estimator, this is not the case that we cannot never, I mean, we never get some kind of the true value. If we basically have like tons of these samples, then we can still get closer to the true values. But this is just not the case that we are having some kind of the expected value of the estimator, which is not exactly matching the the true value. So we need to get the sense of like what's the difference between the unbiased estimator and the biased estimator. So even with the biased estimator, while the expected value does not match the interval, if we have like tons of samples, then the estimator will basically converge into basically the true value. So in terms of the biased estimator still can be useful. So especially the bias estimator can be still useful when we can see that it converges much faster than the unbiased estimator. This is only for the estimating variance. Only for I couldn't get the question. This is only for estimating the variance and not its expected value. Can you elaborate this question? Yeah, I couldn't get the meaning of the question here. So let me first move on while we are working on this question. So this is the thing. While the bias estimator does not have the expected value basically matching the interval, so the case it can be more useful is basically when it basically converges like more faster than the unbiased estimator, while still getting close to the correct results. So let me give you some kind of example for this. So let's think about very simple the case. So we are basically taking some kind of the IID samples from a uniform distribution from the range from the A to B. So before we get into some more details of like this example, let's briefly first check like when you have some kind of like one single sample, which is samples from the uniform distribution, what's the expected value and also the variance of like this random variable. Can you quickly derive this first? Yeah, from the definitions of the expected value and the variance, you can quickly derive all the things. So you can see that the mean becomes like this, and the variance becomes like this, like squared like b minus a over 12, right? See, so yeah, based on this, like what we can see is that like let's think about like very simple the example, which is not that kind of a practical the case, but let's think about that we want to basically mean of this kind of the uniform distribution, the random distribution over this kind of interval from the 0 to 1, not to the A to B. Let's think about like uniform distribution over the interval from the 0 to 1, and we are measuring this kind of the mean using some kind of the some samples that are drawn from the uniform distribution. So we have like n number of samples. And then let's think about like this kind of two estimator. The first one is like more basically, intuitive the way to estimate this the mean of the uniform distribution, right? Just like taking the mean of all the samples. But the thing is that the other way around to basically have this kind of like having the estimator for this mean of the uniform distribution is just taking the maximum value and then taking the half of the maximum value. Then what we can see is that for the first estimator, which is like looks more intuitive, the output we can get is that for the mean, yeah, the expected value of this estimate basically matches the ground truth, basically true value that we want to get, right? But for the and also the variance, we are basically getting the this variance, which is basically showing that the variance is basically proportional to the 1 over the number of samples, right? But for the second estimator, as you can guess from the form of this estimator, it becomes hard to expect that the expected value of like this estimate basically matches the true value. So typically, we get some kind of the value which is smaller than the real value. But actually, we can see that this estimator converges much faster than the estimator. So I'm going to skip some details because the derivation of the expected value and the variance in this case is like much more complicated. But what we can see is that the expected value of this estimator becomes like the 1/2, the 1 second times like n over n plus 1. Which means that when the number of sample is smaller, we're gonna get the expected value which is smaller than the true value. But as you can see, like when we basically increase the number of samples to the infinity, obviously this estimator will also converge to the right value. While when we see the variance, actually the variance is now proportional to the 1 over the squared the number of samples, which means that while this one has the expected value, which is smaller than the true value, the variance basically decreases much faster with the number of samples. So this is kind of a good thing. So for those kind of the cases, when you see that the estimator basically can converge it faster, while it is like biased, that we can consider using this kind of estimator in terms of like having some kind of the more efficiency. So this is kind of the some of the cases that we can also consider some kind of the biased estimator as well. Any questions on this? So this is basically all about basically how we can guarantee to basically get some kind of the correct answer with this kind of the estimate, while we also achieve some kind of the efficiency, like getting closer to this kind of some true value as fast as possible, right? So here, all the question is basically how we're gonna improve this kind of efficiency of the estimates. So the typical way that we are basically achieving this kind of the efficiency is to basically have some kind of having some good sampling this strategy. So let me briefly discuss some kind of the two ideas for the sampling this strategy. Like one is the stratified sampling. So here the idea is that how we can basically decrease the variance of the estimate. For that, like one way we can do is that we are basically partitioning given the domain of the interval into some kind of the non-overlapping regions like this, and allocating samples for each of the region. And then while we basically once we basically compute the estimate for each of the region, which is also called the stratum. So once we compute the estimate for each of the stratum, we sum them up to get the final estimate. And let's briefly see like why this kind of stratified sampling is better in terms like decreasing the variance. So let's assume this kind of simple case, like for some kind of simplicity, let's assume that given the domain of the interval is defined like this kind of the simple bounding box, and then we are having the m stratum, basically partitioning the region into the number of the non-overlapping regions. And let's say Vi is kind of the fractional volume of each of the stratum, basically some kind of the ratio of each of the volume for each of the stratum. Then let's think about a simple case that we are distributing the number of the samples based on this fractional area of each of the stratum. So let's say like the Ni, which is the number of samples for each of the I stratum, is defined as kind of like Vi times the total number of the samples. And also, we're going to use some kind of a simple way that we are defining the probability density function for each of the stratum as kind of the uniform distribution over there. Then now we can define the Monte Carlo estimates like this. So we are basically defining the final estimate as kind of the sum of the estimate for each of the stratum. And for each of the stratum, based on even the definitions of the Monte Carlo the method, we are having this the estimate. So this is basically the estimate. So this is the case that we are having the uniform distribution, right? So as we have the B minus A in the previous slide here, we are having the Vi here. And if we take the sum of all the estimates, that becomes the final estimate, right? So given this kind of the Monte Carlo estimate with the stratified sampling, and when you also know that the mean of each of the random variable and also the variance of each of the the value of the random variable and also the variance of the random variables are defined as like this. when you have this information, what is the variance of like this final the estimate? Can you quickly calculate this? So since we are running out of time, maybe you can check out the answer later. So I will also like post these slides in the course web page. So you're gonna see that we end up getting this So here basically we cancel out this ni with this. Here we have seen that this ni is basically n times vi. So we can basically cancel out this, and we end up getting this, right? So we can see that the variance of like this estimate basically has this form. While if we compare this with the unstratified sampling case, so unstratified sampling is basically not dividing the region into some kind of the strata, small regions, but just having the uniform samples over the entire the space, right? And just for the sake of the comparison, actually this unstratified sampling can be seen as kind of the cases that we are sampling each of the stratum first, and then conditionally sampling each of the point for each of the stratum. So this is kind of equivalent. So just for the sake of like comparison, if we basically also derive the variance based on this kind of the conditional cases, then we can see that actually the variance of like this unstratified sampling case have this kind of the variance, which is basically the case that we are having some kind of the additional term here, which is the non-negative value. So from this, like what we can see is that I just skip some details here, but when you compare these kind of the two variants, so like this for the stratified sampling decrease, and also for the unstratified sampling decrease, what we can conclude is that from the stratified sampling, this basically stratified sampling, the dividing region into the multiple some small pieces never increases the variance. So which means that stratified sampling is always better than any kind of unstratified sampling. And also we can further reduce the variance when you have some kind of the more like finer grain, this kind of strata. So when you basically more like dividing the region into the smaller pieces and allocating the samples, strategically for each of the stratum, we can always have some kind of the better results in terms of like having the much faster the convergence of the estimate. So I'm not sure whether you can see the difference between these two. The left one is basically the case that we are using the unstratified sampling to render this image. And the right one is the case that we are using the stratified sampling for it to render this image. I'm not sure whether you can tell the difference between these two, but I recommend you to check out by downloading these slides and see in your screen whether you can see some difference between these two. Okay, so I will also post all the slides in our course webpage. And next time we're gonna continue discussing some kind of the ideas in terms of improving the efficiency of the estimates. And we're gonna also get into basically how we're gonna utilize this kind of the idea in our kind of the rendering the pipeline. So that's what we are going to discuss the next Wednesday. And if you have any questions, please feel free to post the questions on Slack, and then I will continue this thing next Wednesday. Okay, thank you. Bye.